Have you ever wondered if you could travel back in time and change the past? Would the universe even allow it? What if your future self were to intervene at a crucial moment in your own life? Could such a paradoxical event truly unfold? Imagine a cold, moonless night where the mist hangs heavy, swallowing all sound and vision. You step onto a road and barely notice the car approaching until it's too late. At that precise moment, a stranger, a figure seemingly out of nowhere, pushes you to safety, sacrificing their own life in the process. Later, you receive an envelope taken from the pocket of this mysterious savior. It's addressed directly to you. Inside, just two cryptic words: study physics. Compelled by this profound act of sacrifice, you dedicate your life to unraveling the mysteries of the universe, eventually becoming a celebrated physicist, specializing in Einstein's theories of relativity. Decades of persistent research culminate in a groundbreaking discovery: the world's first functional time machine. Only at this moment does a clarity strike like lightning. You understand your true purpose. You carefully retrieve the letter from its honored place on your wall, place it back in the envelope, and step into the humming device. Your destination? That exact misty night years ago. Now it's you who emerges from nowhere, pushing your younger self away from death's embrace, your own life ending in a paradoxical act of sacrifice. Yet beyond the narrative lies a tapestry of profound scientific questions and paradoxes. Who in fact authored that note? The letter, handed from future to past and back again, seems to exist without an origin, a perfect illustration of the enigmatic bootstrap paradox. And what of the endless loops of your existence? Your act of self-rescue perpetuates a continuous cycle, your life repeating endlessly. But the note? Does it age eternally, becoming more worn each cycle? Here emerges the restoration paradox. Moreover, whose original idea was it to study physics? This thought seemingly appears from thin air, challenging the very concept of cause and effect, a phenomenon known as the ex nihilo paradox. This scenario also deeply questions the nature of free will. If your fate is predetermined by the necessity of building the time machine to save yourself, does this mean your choices were never truly your own? This defines the predestination paradox. And finally, what happens if you refuse this cycle, if you attempt to break the loop? You swiftly encounter the auto-infanticide paradox. You can't abstain from saving your younger self, because without surviving, you cannot exist to even contemplate such rebellion. These intriguing puzzles illustrate the compelling complexity of time travel, challenging the very fabric of reality. While freely traveling through time remains beyond our current grasp, modern physics does hint at tantalizing possibilities. Could these temporal paradoxes be resolved within our lifetime? And what would it mean for our understanding of reality? Welcome to the captivating intersection of imagination and physics, where possibility dances at the edge of discovery. The Block Universe, a scientific inquiry into the nature of time. In the dense equatorial rainforests, where the reverberating cries of howler monkeys pierce the thick, moisture-laden air, one can drift along the serpentine course of a muddy river, passively borne by its unyielding current. The river, winding and unceasing, propels the canoeist forward without the need for paddles, offering a vivid metaphor for the human experience of time. This very analogy was employed by the acclaimed time travel author Jack Finney, who likened our temporal journey to such a river, continuous and inescapable, carrying us from a bygone past toward an unfolding future. Yet this metaphor invites deeper reflection. What becomes of the segments of the river we have already traversed? In temporal terms, where does the past reside once it has ostensibly passed? And what of the future? Does it exist only in potentiality until we arrive at it? To suggest that the upper reaches of a river vanish once one rounds a bend would be absurd. Likewise, to posit that time is only real in the present moment, while the past and future vanish or remain unreal, appears equally tenuous under scrutiny. This line of questioning leads us to a profound ontological and physical proposition, that all moments in time, past, present, and future, are equally real. This notion, known in philosophy as eternalism, stands in stark contrast to presentism, which asserts that only the present is real, with the past relegated to memory and the future to imagination. While this debate stretches back to ancient Greece, with Saint Augustine famously pondering the elusive nature of the present, it has since evolved into a cornerstone of theoretical physics through what is known as the block universe theory. The block universe posits that time is not a fleeting phenomenon, but a dimension akin to space. Just as all points in space coexist regardless of our position, so too do all moments in time. The universe is envisioned as a four-dimensional block composed of three spatial dimensions and one temporal dimension. Within this block, every event that has ever occurred and will occur is fixed, laid out in an immutable geometry of space-time. This view derives robust support from Einstein's theories of relativity, particularly the special theory of relativity, published in 1905, and the subsequent general theory of relativity in 1915. The former shattered the Newtonian notion of absolute time, a universal clock ticking uniformly for all observers. Instead, Einstein demonstrated that time is relative, contingent upon an observer's velocity and gravitational environment. Consequently, two observers in different states of motion may disagree on the sequence of events, with one asserting that event A precedes event B, and the other claiming the reverse. These disagreements are not due to error, but are both valid within their respective frames of reference. This relativity of simultaneity undermines the presentist view. If one observer's past is another's future, then the very distinction between past and future becomes illusory. The events we consign to history may, from a different vantage, still be to come. Such implications necessitate a model of the universe in which all events coexist, a block in which temporal locality, like spatial locality, is merely observer-dependent. Further development of these ideas came from Hermann Minkowski in 1908, who geometrized Einstein's insights by proposing that space and time are not separate entities, but components of a unified space-time manifold. According to Minkowski, objects in motion experience distortions in their measurements of time and space because they are navigating through this four-dimensional fabric. The concept of time as an independent backdrop was abandoned in favor of a geometric structure in which time is treated as a coordinate akin to spatial coordinates. The transition from theoretical proposition to empirical validation came with general relativity. Here, Einstein introduced the concept of gravitation, not as a force in the Newtonian sense, but as a manifestation of the curvature of space-time. To visualize this, imagine space-time as a taut rubber sheet, with massive objects creating indentations. Smaller objects follow the curves of this sheet, appearing to orbit due to the geometry rather than an attractive force. One of the first critical confirmations of this framework came from an astronomical anomaly noted decades earlier. In the 1840s, astronomers had successfully used Newton's laws to predict the existence of Neptune based on perturbations in the orbit of Uranus. Yet the orbit of Mercury, the innermost planet, defied complete explanation. Its perihelion precession exceeded predictions by Newtonian mechanics. Efforts to attribute this discrepancy to an unseen intramercurial planet failed. It was Einstein's equations that provided the correct adjustment, accurately predicting the anomalous precession as a result of the sun's intense curvature of local spacetime. This triumph marked a critical empirical success for general relativity and, by extension, for the block universe. Under this paradigm, gravity is no longer a force that pulls, but a natural consequence of geodesics. The shortest paths through curved spacetime, objects in freefall are merely following these paths. In extreme gravitational environments, such as near black holes or neutron stars, the curvature becomes pronounced, resulting in phenomena such as gravitational lensing, time dilation, and even gravitational waves, all observed and confirmed by modern astrophysical measurements. Thus, if space and time are indeed inseparable, and if space-time is a static four-dimensional entity, then the past and future must possess ontological parity with the present. A being capable of perceiving the entire block from outside its dimensional constraints, a hypothetical super-observer, would witness all events, past and future, laid bare like the frames of a film reel. The dynamism of time, our sense of flowing from one moment to the next, would be exposed as a byproduct of consciousness moving along its world line, not a feature of reality itself. From the cosmic perspective, the universe is a tapestry of interwoven world lines, the paths that particles trace through spacetime. You, the observer, are not a static object, but a nexus of countless world lines. Your atoms, thoughts, memories, and experiences are coordinates on this vast geometric structure. Even if your spatial location remains fixed, your temporal coordinate shifts inexorably, propelling you forward in your personal history. But what does this entail for free will, choice, and agency? If every event, from the mundane to the monumental, is already inscribed within the block, then our decisions are not spontaneous acts of will, but predetermined sequences. From your morning coffee to your eventual death, all is charted along your world line. In this sense, the block universe resembles a novel, complete, edited, and published. You, as a character, may not know what awaits in the next chapter, but the outcome is fixed. Yet this deterministic vision is not without complexity. Quantum mechanics introduces probabilistic elements, and debates over whether these indeterminacies undermine the block universe remain ongoing. Some physicists posit a many-worlds interpretation wherein each possible outcome branches into a separate block. Others argue that even quantum events are deterministic when viewed from a higher dimensional vantage. One of the most tantalizing consequences of the block universe is the theoretical possibility of time travel. If time is a dimension, and if all events coexist, then accessing different temporal coordinates becomes at least mathematically conceivable. Just as one might move east or west in space, one might move forward or backward in time. General relativity admits solutions to Einstein's field equations that allow for closed time-like curves, paths through spacetime that loop back on themselves. Such curves imply that a traveler could, under certain conditions, return to an earlier point in their own world line. The canonical example involves rotating black holes, where spacetime can twist upon itself in a way that permits closed trajectories. However, practical implementation faces insurmountable challenges: exotic matter, negative energy, and stability issues. Moreover, the paradoxes introduced by time travel, the so-called grandfather paradox, for instance, remain unresolved, despite efforts to incorporate self-consistency principles, such as those proposed by physicist Igor Novikov. Still, if time travel is forbidden, it is not because it violates the structure of space-time. Rather, it may be due to constraints on energy, entropy, or information preservation. Theoretically, nothing within the framework of general relativity outright prohibits it. In sum, the block universe is more than a poetic idea. It is a robust, mathematically supported model with far-reaching implications for cosmology, ontology, and the human experience. The Big Bang, which we often consider the beginning of everything, is better understood not as a temporal start, but as the boundary condition of space-time itself, the origin point from which all four dimensions unfurled. Just as a globe has poles, the universe may have temporal boundaries, but everything in between exists simultaneously within the block. Ultimately, our perception of time as passing is not a reflection of objective reality, but a consequence of our neurological processing. The arrow of time, defined by entropy and memory, flows in one direction, but space-time itself is directionless. It simply is. As beings embedded within this vast geometric edifice, we are both prisoners and interpreters of time. We cannot step outside the block, but through physics, we may glimpse its contours. In doing so, we understand that we are not merely adrift in time's river. We are inscribed within its very bedrock. Visiting the Future, a scientific odyssey through time dilation and cosmic extremes. Amidst the grand stage of the cosmos, where gravity sculpts galaxies and light bends under the weight of mass, we find ourselves tracing a single particle, a lone proton, on an epic voyage through space and time. Born in the heart of a galactic catastrophe, this subatomic projectile races toward Earth at a velocity infinitesimally shy of light speed. Propelled by forces almost unimaginable in magnitude, it embodies one of nature's most enigmatic phenomena, the ultra-high energy cosmic ray. This particular proton, accelerated perhaps by a supermassive black hole tearing through a galaxy, possesses an energy 100 quintillion times greater than that of a typical photon. When it finally crashes into Earth's upper atmosphere, having crossed more than 1 billion light-years of intergalactic void, it does so with an energy surpassing the collisions orchestrated by the Large Hadron Collider by a factor of 21 million. It was this staggering collision that led scientists to christen it the "Oh my God" particle. Yet, beyond its evocative name lies a profound scientific implication. This particle is not merely a curiosity. It is a cosmic messenger, reminding us that Earth is not a sealed sanctuary, but an exposed target in a celestial shooting gallery. The aftermath of such a collision is invisible to the naked eye, but no less spectacular. A cascading shower of secondary particles, pions, muons, neutrinos, rains down through the atmosphere in a relativistic firework of decay and transformation. Among these secondary fragments, muons are of particular interest. These particles are born unstable, with a half-life of merely 1.56 microseconds in their own rest frame. Yet, against all odds, vast numbers of muons survive the descent from the upper atmosphere to Earth's surface, an enigma that puzzled early physicists until the mid-20th century. It was Bruno Rossi, a visionary Italian physicist, who illuminated the paradox. His fieldwork, conducted high in the Rocky Mountains of Colorado, yielded data that would become foundational in experimental relativity. At Echo Lake, perched at an altitude of nearly 2,300 meters, Rossi detected more muons than classical Newtonian mechanics would permit. Even accounting for their high velocities, exceeding 98% the speed of light, the statistical survival rate of muons should have been vanishingly small by the time they reached his instruments. How could such a short-lived particle, created tens of kilometers above Earth's surface, persist long enough to be detected at altitude? The answer lies in Einstein's special theory of relativity, and specifically in the phenomenon known as relativistic time dilation. In essence, special relativity posits that the space-time budget available to any object is constant and bound by the speed of light. This budget must be distributed between spatial motion and temporal progression. The more an object moves through space, the less it experiences the passage of time. Thus, for a muon moving at near light speed, time quite literally slows down relative to an observer on Earth. From the muon's own perspective, its journey to the surface is swift. Not enough time passes for it to decay significantly. To the earthbound observer, it seems as though the muon defies its half-life. But both realities are true in their own frames of reference, reconciled through the equations of Lorentz transformations. Bruno Rossi's high-altitude muon experiments were among the first empirical demonstrations that time dilation is not a theoretical abstraction. It is a measurable, verifiable feature of our universe. His work thus provided the first credible evidence that travel into the future via relativistic effects is not only possible, but inevitable for objects in high-speed motion. But does this phenomenon truly constitute time travel? To explore this, let us conduct a thought experiment grounded in physical law. Imagine you are the muon. Instead of a direct plunge from the upper atmosphere to Echo Lake, suppose you embark on a loop around the universe at 98% of the speed of light, relative to observers who remain at rest. When you return home, only 25 years have elapsed for you. But for those who stayed behind, moving far more slowly through space-time, 125 years have passed. You have effectively leaped forward in time. Your subjective experience is disconnected from the chronological sequence on Earth. This temporal leap is not a speculative notion. It is a direct corollary of the equations that govern relativistic motion. Such relativistic travel fundamentally alters the generational continuity we take for granted. In Ken Liu's poignant short story, Memories of My Mother, this effect becomes the emotional and narrative fulcrum, exploring how family bonds stretch and sometimes break under the tension of time passed at different rates. The implications of relativistic time dilation are not confined to hypothetical journeys. They are present in the here and now. Consider the twin astronauts Mark and Scott Kelly. Mark, born 6 minutes before Scott, remained on Earth, while Scott spent over 500 days aboard the International Space Station. Though their difference in biological age is minuscule, just 5 milliseconds, Scott is technically younger than his twin due to his greater time spent moving at high speed through space-time. Had Scott traveled at muon-like velocities, the effect would be magnified dramatically. A 6-minute age gap could become a disparity of 6.5 years. The relationship between time and speed becomes strikingly evident through such real-world comparisons. Yet velocity is not the only agent capable of dilating time. Gravity, too, warps the flow of time, albeit via a different mechanism. Enter gravitational time dilation, a phenomenon arising from Einstein's general theory of relativity. In this framework, mass curves the fabric of space-time itself, creating wells of gravitational potential. Time flows more slowly the deeper one resides within such a well. To visualize this, imagine two identical light clocks, devices made from parallel mirrors that tick whenever a photon bounces between them. One clock remains on Earth's surface, while the other is taken deep into a gravitational well, say near a black hole. The photon within the lower clock must traverse a longer curved path due to the distortion of spacetime. As a result, it ticks more slowly, Upon returning both clocks to the same location, the one that experienced stronger gravity will have aged less. In principle, this is yet another method to travel into the future. Descend into an intense gravitational field, perhaps near the event horizon of a supermassive black hole, then return. Upon your reemergence, more time will have elapsed for the universe than for you. This concept was not only central to Kip Thorne's scientific advisory role in the film Interstellar, it remains an active field of research in relativistic astrophysics. Interestingly, Earth itself produces a modest gravitational well, and this too affects time. When Rossi ascended Mount Evans, he was physically climbing out of Earth's gravitational grip. Even at that altitude, time ticked imperceptibly faster for him than it did at sea level. The difference is minuscule, only detectable using the most precise atomic clocks, but it is real. In 2022, physicists performed one of the most delicate measurements of this effect by placing two ultra-precise atomic clocks just 1 millimeter apart. The difference in gravitational potential across that tiny vertical span was sufficient to cause a measurable divergence in their ticking rates. That level of sensitivity illustrates how deeply embedded relativistic time dilation is in our universe's structure. Indeed, many of us experience time dilation indirectly every day through technologies like GPS. The satellites orbiting Earth function as a constellation of timekeepers, each equipped with atomic clocks. These satellites are subject to both forms of time dilation. They move rapidly and reside further from Earth's gravitational center. Without compensating for these effects, GPS signals would quickly drift out of sync, rendering location tracking hopelessly inaccurate. To summarize, time travel into the future is not only theoretically plausible, it is already woven into the fabric of experimental science, technological infrastructure, and observational cosmology. Whether by accelerating to relativistic speeds or dwelling in strong gravitational fields, forward time travel is supported by a century of empirical validation. It is, in every sense, a scientific fact. What remains elusive, however, is the inverse journey. Time travel into the past. Can one reverse the arrow of time, swimming upstream through the entropy of the cosmos? That, as of now, remains a question unanswered. Visiting the past, the scientific pursuit of time reversal in a relativistic universe. In the annals of recent history, 2011 may seem mundane. Barack Obama sat in the Oval Office. Prince William and Kate Middleton had just tied the knot. And NASA's space shuttle Atlantis performed its final descent, closing the chapter on a golden era of American spaceflight. Yet amidst the geopolitics and pop culture, a momentous scientific announcement reverberated through the physics community. From a facility deep beneath the Italian Apennines came a claim so audacious it threatened to overturn the very bedrock of modern physics. Physicists working on the OPERA experiment, oscillation project with emulsion tracking apparatus, declared that they had observed a phenomenon that should be impossible. Neutrinos, ghostly subatomic particles capable of passing unhindered through planets, appeared to have exceeded the speed of light. According to their measurements, these neutrinos, sent from CERN in Geneva, Switzerland, to the Gran Sasso Laboratory, 730 kilometers away, had arrived approximately 60 nanoseconds earlier than a light-speed journey would have permitted. This finding would not merely violate Einstein's special theory of relativity, it would shatter the conceptual framework of causality itself. The speed of light, as Einstein established in 1905, is the universal speed limit. Any particle with mass, as it accelerates toward that boundary, requires exponentially more energy. At the speed of light, its relativistic mass approaches infinity, and the energy needed becomes unbounded. As such, no massive object may ever surpass this velocity. Light speed, then, is not just a limit. It is a law of nature. And by that law, nothing should move faster. Within a year, the physics community unraveled the anomaly. A faulty fiber optic cable in the opera detector had created a timing offset. The neutrinos, it turned out, had obeyed the speed limit after all. Yet the excitement, perhaps even the hope, that filled the scientific world during those months pointed to something deeper, the longing to crack open the gates of time and walk backwards through its corridors. Why did this matter so much? Because if faster-than-light travel were possible, then backward time travel might be possible too. The relationship between velocity and temporal direction is encoded into the very structure of spacetime. This linkage first emerged not from science fiction, but from rigorous mathematics. In 1937, Dutch physicist Willem Jacob van Stockum published a paper entitled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry." Though its title was obscure, its implications were revolutionary. By solving Einstein's field equations, van Stockum demonstrated that rotating distributions of mass could give rise to what are now known as closed time-like curves. In spacetime physics, a world line represents the path of an object through space and time. For most of us, that world line is a unidirectional arrow from birth to death, from past to future. But a closed time-like curve is a loop. It returns to its own past. An object traversing such a path might encounter earlier versions of itself, or revisit moments it had already experienced. In van Stockum's model, the fabric of spacetime permits such loops under certain conditions. Time travel to the past, it seemed, was not forbidden by the equations of general relativity. But there is a catch. To close a time-like curve, to fold the arrow of time back upon itself, one must leave the region of spacetime known as the light cone. The light cone defines the limits of causal influence. Suppose you are stationary at a given point in space and time. The future light cone delineates the regions of spacetime that you can reach, assuming nothing travels faster than light. Conversely, the past light cone defines the regions that could influence your present. To reach a point outside this cone would require superluminal travel. Therefore, to loop your world line back into your past would seem to necessitate moving beyond the speed of light, something the laws of special relativity strictly prohibit. Yet there is another, more subtle path. If the space-time around you were warped in just the right way, your light cone itself could tilt. You would not need to leave the cone. Rather, the cone would rotate around you, as long as your trajectory always remained within the local light cone. You could theoretically circle backward through time without ever exceeding the cosmic speed limit. This is not mere speculation. In 1974, American physicist Frank J. Tipler explored such a solution. He analyzed what would happen if an extremely massive cylinder containing at least 10 solar masses were rotated at relativistic speeds along its longitudinal axis. His calculations showed that under these conditions, space-time around the cylinder would become so twisted that light cones near it would tilt dramatically. Following a precisely calculated spiral path around the cylinder, a spacecraft could return to an earlier point in time. But there are complications. To make the mathematics tractable, Tipler assumed the cylinder was infinitely long. A finite version may not produce the same effect. Moreover, the rotational velocity required is astronomical, billions of revolutions per minute. This, coupled with the need for exotic conditions, makes the Tipler cylinder more of a thought experiment than a blueprint for a time machine. Then, in the 1990s, Stephen Hawking introduced a profound constraint. He argued that attempts to construct closed time-like curves in realistic settings would inevitably require negative energy, a bizarre and elusive substance that defies classical intuitions. Here enters quantum field theory. While classical physics forbids negative energy, quantum mechanics introduces nuances. In the quantum vacuum, virtual particles continually flicker in and out of existence. These pairs can momentarily borrow energy from the vacuum, creating local zones where energy density drops below zero. It's like dipping briefly into an overdraft. Nature allows it, but only transiently and within limits. Such fleeting phenomena suggest that negative energy is real, but its utility is constrained. It might allow the formation of microscopic time loops or fluctuations, but engineering a macroscopic, human-sized portal to the past seems vastly out of reach. Yet one theoretical construct continues to kindle scientific imagination: the wormhole. Popularized by Carl Sagan's novel Contact, the concept of a wormhole originated in the equations of Einstein and Rosen. Sagan, in crafting a scientifically plausible narrative for interstellar travel, consulted physicist Kip Thorne, who proposed that a wormhole, a bridge through spacetime, could be used to traverse vast distances without violating the light speed constraint. Imagine spacetime as a sheet of paper. Earth is at one corner, and Vega, a star 25 light-years away, is at the opposite edge. Rather than traversing the sheet linearly, you fold it so the 2 points touch. A wormhole is that fold. Step through it, and you arrive at Vega instantaneously, not because you traveled faster than light, but because you circumvented the intervening space. Now extend this concept further. Suppose the two mouths of a wormhole are placed at different gravitational potentials or moved at different velocities. Due to relativistic time dilation, the clocks at the two ends will desynchronize. If you later traverse the wormhole, you can emerge at a point in the past, relative to the departure point. In theory, you could return to Earth before you left. However, engineering such a wormhole is far from trivial. Just as with the Tipler cylinder, the wormhole throat would be prone to collapse unless propped open by negative energy or exotic quantum fields. Thorne and his colleagues investigated this scenario and concluded that the gravitational stress of a traveler passing through would tend to destabilize the wormhole. Nonetheless, physicists have proposed potential stabilizing mechanisms, from quantum entanglement to magnetic tension. Speaking of entanglement, it too has been linked to speculative ideas of backward causality. Quantum entanglement allows particles to remain correlated across vast distances. A change to one instantaneously affects the other. While this appears to imply faster-than-light communication, it does not permit usable information to be transferred this way. The paradox of spooky action at a distance still respects relativistic causality. However, in the speculative realm of closed time-like curves and negative energy densities, researchers continue to ask, might entanglement be a stepping stone to time travel mechanisms not yet understood? In 1991, physicist J. Richard Gott proposed that cosmic strings, hypothetical defects in the fabric of spacetime formed during the early universe, could be harnessed to create time loops. If two cosmic strings passed each other at relativistic velocities, the resulting spacetime geometry could allow for closed time-like curves. Once again, immense energies and precise trajectories would be required. These are not technologies we can build, but solutions to Einstein's equations that suggest such configurations are not forbidden. Still, we are left with the troubling implications of retrocausality. If time travel to the past were ever realized, how would we resolve the paradoxes? Could you prevent your own birth? Could you stop the neutrino measurement that made time travel possible? Would such contradictions unravel the fabric of logic? One interpretation, drawn from quantum mechanics, is the many worlds hypothesis. If every quantum event branches into a separate reality, then any action taken by a time traveler merely creates or enters a different universe. The original timeline remains untouched. This avoids contradictions, but comes at the cost of a potentially infinite multiverse. Alternatively, the Novikov self-consistency principle posits that time travel to the past is possible, but only if the actions of the traveler are already part of history. You may attempt to alter the past, but whatever you do will only fulfill events that have already occurred. The laws of physics, it seems, may tolerate closed time-like curves only if they do not permit paradoxes. For now, time travel to the past remains a speculative frontier. Unlike forward time travel, which is an experimentally confirmed phenomenon grounded in relativity, the journey backward requires conditions, energies, and materials not yet accessible to human civilization. Still, the theoretical doors remain ajar. From rotating cylinders and cosmic strings to wormholes stabilized by negative energy, the blueprints for time machines, however improbable, exist within our current physical theories. Whether the future of science will ever unlock the engineering secrets necessary to manifest these structures is unknown. But one thing is certain: the universe, in its elegance and complexity, has not definitively closed the door on visiting the past. Time streams, quantum realities, and the fluid boundaries of causality. You sit, shackled and sweating, beneath harsh lights in a sterile observation room. Before you, a glass vial containing a lethal gas perches delicately beneath a hammer affixed to a robotic arm. The mechanism is not designed for mercy. It is tethered to a quantum sensor, a device measuring subatomic particles, particles whose nature is cloaked in uncertainty. Each moment, a measurement is made. The particle collapses into one of two possible states, A or B. If the result is A, nothing happens. If it is B, the hammer falls and the vial shatters, ending your life. This is not merely an experiment in survival. It is a demonstration of probability stretched to its cosmic limits. The machine is set to perform 100 measurements. Each has a 50% chance of resulting in your demise. The odds of surviving all 100 consecutive measurements are staggeringly small, approximately 1 in a million trillion trillion. And yet, somehow, you survive. Unwittingly, you have participated in a quantum variation of Schrödinger's cat. Unlike the original feline subject sealed in a box, you are fully conscious of your mortality and its dependence on the whims of quantum collapse. But according to one radical and increasingly influential interpretation of quantum mechanics, your survival is not merely good fortune. It is evidence, tangible and experiential, of a far deeper truth, that reality is not singular, but forever bifurcating. This interpretation, known as the many worlds interpretation, was proposed by physicist Hugh Everett III in 1957. According to MWI, every quantum event with multiple outcomes causes the universe to split, creating parallel branches in which each possible outcome actually occurs. Measurement does not collapse a wave function. It divides the observer along with the universe. In your case, there were 100 quantum events, 100 moments in which the universe could have split. With each measurement, two possibilities unfolded, generating 2,100 branches of reality. In most, the vial shattered and your life ended. But in one timeline, the one you now inhabit, you survived every measurement. This thought experiment, often dubbed quantum immortality, is not designed to suggest that you are invincible. Rather, it demonstrates that, from a subjective point of view, there is always one branch, one stream, where you continue existing, however improbable it may be. All other versions of you perish in their respective branches, but your consciousness never experiences that cessation. In some interpretations, this constitutes a kind of observer-bound immortality. But the significance of MWI extends beyond philosophical musings on death. It may offer a compelling resolution to the profound and often paradoxical nature of backward time travel. Among the most notorious of time travel paradoxes is the grandfather paradox. You travel back in time and kill your grandfather before he fathers your parent. This act negates your own existence. But if you were never born, how could you have traveled back in time to commit the act? The logical contradiction loops endlessly. To reconcile such dilemmas, physicists and philosophers have proposed a range of theoretical mechanisms. Stephen Hawking's chronology protection conjecture posits that the laws of physics conspire to prevent backward time travel altogether. According to Hawking, the universe enforces a form of cosmic censorship. Causality is protected, and any attempts to build a time machine will inevitably fail, whether through quantum instability, energy feedback, or disruption from virtual particles. An alternative to Hawking's preventive mechanism comes from Igor Novikov, who in the 1980s proposed the self-consistency principle. In this model, time travel is allowed, but you cannot change the past. The timeline is self-consistent. Any actions taken by a time traveler must already be part of history. For instance, if you go back to attempt to kill your grandfather, something will prevent you from succeeding. The gun may jam, or you may lose your nerve, or your grandfather escapes. Either way, causality remains unbroken. However, self-consistency can become strained under more complex conditions. Consider an elegant paradox developed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser in a series of papers between 2020 and 2022. Imagine a simple universe populated by color-changing balls, white and black spheres that reverse color upon collision. If a black ball travels back in time and collides with its past self, both become white. But if the ball is now white, how did it become black in the first place to initiate the loop? The system becomes inconsistent. Here, Novikov's model struggles, but MWI provides a possible solution. The ball doesn't travel back into its own past. It enters a parallel timeline. The ball that emerges from the time machine is not the same one that entered it. It belongs to a different branch of reality. Thus arises the concept of time streams, an extension of the many worlds model into the domain of time travel. When you travel backward in time, you do not alter your original timeline. Instead, you enter another version of the universe where the past plays out differently. The grandfather you murder is not your biological progenitor, but a parallel version in a different stream. Your own existence in your original stream remains intact. This branching model of time provides a framework in which free will can coexist with time travel. In your stream of origin, the past remains fixed and immutable. But once you cross temporal boundaries, you are free to act in the new stream, untethered by constraints of causality from your native timeline. The implications extend to other classic paradoxes, such as the bootstrap paradox, where information or objects are trapped in a loop with no discernible origin. Imagine you receive a mysterious letter from your future self warning of a life-altering decision. You follow its advice, become a physicist, and eventually travel back in time to deliver the same letter to your younger self. Who wrote the letter originally? Within a many worlds framework, this can be resolved. The original you in time stream A writes the letter and sends it to stream B, where a younger version receives it and grows up to become the same time traveler who now delivers the letter to stream C. The paradox is dissolved because each act occurs in a separate, parallel timeline. The letter has a point of origin. It is simply obscured by the crossing of streams. this may seem an extravagant explanation, invoking multiverses and infinite branches to account for what might be seen as a conceptual quirk. Critics, including John Wheeler, who coined the term wormhole, have expressed concern about the metaphysical baggage carried by many worlds interpretations. Yet even Wheeler acknowledged the utility of these ideas in grappling with the quantum behavior of reality. The physicist Bryce DeWitt, a prominent advocate of MWI, once remarked, "Every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe, is splitting our local world on Earth into myriad copies of itself." According to this view, reality is an ever-branching fractal of possibilities. Every decision, every quantum fluctuation, every measurement fractures the river of time into countless tributaries, each flowing forward along its own logical trajectory. This continual bifurcation does not imply chaos, but a multiplicity of determinisms, each consistent within its own framework. In this vision, the universe is not a line, but a vast, recursive tree of time, expanding eternally with every choice, every quantum possibility. Thus, time travel to the future is no longer a question of theory. It is a proven consequence of relativistic time dilation, whether via velocity or gravity. We know that time can pass at different rates for different observers. Atomic clocks aboard GPS satellites must be calibrated to account for these effects, or our maps and directions would fail. Travel to the past, however, remains speculative, permitted by some equations, constrained by others, and steeped in interpretive uncertainty. Whether via wormholes stabilized by exotic matter, or rotating cylinders twisting spacetime into loops, or simply by quantum transitions into parallel time streams, we have models that permit backward motion through time, but no empirical evidence as yet. And so we return to our solitary observer, the one version of yourself who survives the impossible quantum trial. From your perspective, this is the only reality. The others, those where the hammer fell, exist beyond your awareness, but not beyond the scope of physical theory. You are not lucky. You are simply the self that continued to be conscious in a universe where you could. This is the haunting, beautiful power of many worlds. Every possibility is realized, and you, like all observers, are merely riding one thread of an ever-branching tapestry. As we drift along our respective world lines through the four-dimensional fabric of space-time, the past may not be behind us in any absolute sense. It may yet persist, alive in other timelines, accessible perhaps by methods we have not yet discovered. Until then, we traverse the present with memories of the past and dreams of the future, aware that the universe is far stranger, more fragmented, and more wondrous than we have yet dared to imagine.
What would it be like to fall into a black hole? Would you be able to perceive its boundaries, or would reality itself begin to dissolve around you? And what role do these cosmic behemoths play in shaping the very fabric of the universe? To answer these questions, we must journey to one of the most enigmatic and extreme regions of space, the heart of our own galaxy, where an immense and invisible force dominates its surroundings. At first glance, the region appears deceptively bright. Unlike the vast emptiness of interstellar space, the galactic core is a crowded and chaotic place. A dense concentration of stars, millions of them, whirl in complex orbits, their trajectories tracing an invisible gravitational master. At the very center of this celestial ballet lies Sagittarius A*, a supermassive black hole with a mass roughly 4 million times that of the Sun. Unlike an ordinary star, Sagittarius A* is not a visible sphere of light, but an absence, a void so absolute that even light itself cannot escape its grasp. However, its presence is betrayed by the chaotic motions of the stars that encircle it and by the glowing ring of superheated matter spiraling into its depths. This luminous accretion disk, composed of gas and dust stripped from unfortunate celestial bodies, radiates intensely as gravitational forces compress and heat it, unleashing powerful X-rays and gamma rays into space. As you approach this region, the first subtle effect you notice is an inexorable tug, a gravitational pull that intensifies as you drift closer. Soon, you find yourself drawn into an orbit around the black hole, carried along by the spiraling currents of the accretion disk. Here, amidst the swirling chaos, space itself is warped. The immense gravitational forces stretch and distort the very fabric of space-time, creating the illusion that distant starlight bends and loops around an unseen center. Your body is subjected to extreme conditions. Friction from high-energy particles batters you with radiation, shredding your DNA beyond repair. But these physical afflictions pale in comparison to the effects of gravity itself. The closer you move to the black hole's event horizon, the boundary beyond which escape is impossible, the more time itself begins to behave strangely. To an external observer, your descent appears to slow, as if you are falling ever more sluggishly toward the edge. In their frame of reference, you never quite cross the horizon. Instead, you seem to linger indefinitely, your image growing redder and dimmer as gravitational time dilation stretches your wavelengths into oblivion. But from your own perspective, nothing unusual occurs until you finally pass the event horizon and any remaining connection to the universe is severed. Beyond this point, conventional physics ceases to offer a clear explanation. Space and time swap roles. Rather than moving through space toward the singularity, it is now time itself that pulls you inexorably inward. No force, no intervention, nothing in the known universe can halt your fall. What awaits at the center remains an unsolved question. General relativity predicts an infinitely dense singularity, a point where gravity becomes infinite and our understanding of physics breaks down. Quantum mechanics, however, suggests that some yet undiscovered mechanism may prevent such an extreme fate. The existence of black holes, first postulated in 1783, has transformed our understanding of the cosmos. No longer mere theoretical oddities, they are now recognized as fundamental components of the universe. Supermassive black holes like Sagittarius A** are believed to reside at the heart of nearly every galaxy, playing a crucial role in their evolution. The energy released by their accretion disks can trigger star formation or, conversely, suppress it, regulating the growth of galaxies over cosmic timescales. Yet, one of the greatest mysteries remains. How did these supermassive black holes form in the first place? Did they grow from the collapse of the first massive stars, gradually accumulating matter over billions of years? Or were they seeded by exotic processes in the early universe, forming almost simultaneously with the first galaxies? As astronomers peer deeper into the cosmos, they search for answers, hoping to uncover the origins of these enigmatic giants and, in doing so, illuminate the story of the universe itself. The first black hole. Rain lashes against the tin roof of the makeshift shelter, cascading in rivulets down its sides and pooling into the muddy trenches below. A biting December wind weaves through the desolate encampment, its chill gnawing at the weary soldiers huddled beneath the slate-gray sky. The distant echoes of gunfire and artillery have, for now, fallen silent. Inside the dimly lit refuge, a senior lieutenant shifts his focus from the grim realities of war to the stack of dispatches on his desk. The year is 1915. The place, the Eastern Front of World War I. The lieutenant is Karl Schwarzschild. A distinguished physicist and director of the Astronomical Observatory in Potsdam, Schwarzschild was drawn into the war effort, applying his formidable mathematical prowess to the calculations of ballistic trajectories. Yet, tonight, amid the chaos and destruction, something unexpected captures his attention. Among the dispatches, a thick envelope bears the unmistakable handwriting of his colleague and friend, Albert Einstein. Inside lies a paper titled The Field Equations of Gravitation, a work destined to redefine our understanding of the universe. In it, Einstein presents the mathematical scaffolding of what would later be known as general relativity, a theory that describes how mass distorts space-time and how that curvature, in turn, dictates the motion of matter. The equations are intricate, their reasoning recursive, their solutions elusive. Yet, by the flickering light of a lamp, Schwarzschild pores over them with fervor, his mind alight with curiosity. Despite the war raging around him, within days Schwarzschild composes a letter back to Einstein. It contains something extraordinary, a precise and elegant solution to the equations, a discovery that would have profound implications for the nature of gravity and the cosmos itself. In his letter, he writes with characteristic humility, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Schwarzschild's solution describes the curvature of space-time surrounding a perfectly spherical mass. But embedded within it is a prediction that stretches the limits of comprehension. If an object were compressed beyond a critical threshold, later termed the Schwarzschild radius, its gravitational pull would become so immense that nothing, not even light, could escape its grasp. This was, in essence, the theoretical blueprint for what we now call a black hole. The Schwarzschild radius is determined by three fundamental quantities: the universal gravitational constant, the speed of light, and the mass of the object in question. Since the constants remain fixed, the radius depends solely on mass. More mass means a larger Schwarzschild radius. For a human, this critical size would be roughly a millionth the diameter of a single quark, an unfathomably tiny scale. For Earth, it measures just 9 millimeters. For the Sun, approximately 3 kilometers. However, since real-world celestial bodies exist far beyond these minuscule thresholds, their gravity remains within normal bounds. Only under extreme conditions, where matter is compacted into an inconceivably small volume, would Schwarzschild's prediction take tangible form. Though Schwarzschild's intellect endured the horrors of war, his body did not. He succumbed to a debilitating illness before he could witness the full ramifications of his discovery. For years, the idea of such an object, one where space-time curvature became infinite, was dismissed as an abstract mathematical curiosity. Many physicists resisted the notion that such an entity could exist in nature. That skepticism began to wane in 1964. High above Earth's atmosphere, where the protective veil of air no longer blocks high-energy radiation, 2 Geiger counters aboard a rocket flight detected an enigmatic source of intense X-rays in the constellation Cygnus. The object, later named Cygnus X, 1, presented a riddle, a powerful emitter of X-rays, yet invisible to optical telescopes. Further investigation revealed startling properties. The rapid fluctuation of its X-ray emissions on timescales shorter than a second implied a compact size. But orbital measurements of a visible companion star revealed the invisible source's mass, at least 15 times that of the Sun. Such an object was too massive to be a white dwarf or a neutron star. The only plausible explanation was the very entity Schwarzschild had envisioned decades earlier, a black hole. As evidence for Cygnus X, one accumulated throughout the 1970s, the scientific community finally embraced the reality of black holes. The term itself had only recently been popularized. In a 1967 NASA lecture, the physicist John Wheeler sought a more palatable alternative to the cumbersome phrase, gravitationally completely collapsed object. An exasperated audience member proposed a more succinct term, black hole. Wheeler seized upon the name, and it swiftly entered both scientific and popular lexicon. Today, we understand well how black holes like Cygnus X form. Massive stars, sustained by nuclear fusion, eventually exhaust their fuel. Without the outward pressure of fusion to counteract gravity, the core collapses, often triggering a supernova explosion. If the remnant core exceeds roughly 3 solar masses, no known force can resist its collapse, and a black hole is born. Encased within its event horizon, the Schwarzschild radius, lies a region from which no information can escape. The more mass it accrues, the larger it grows, devouring anything that crosses its threshold. Yet, the interior of a black hole remains a mystery. Einstein's equations suggest that at its core lies a singularity, a point where space-time curvature becomes infinite and conventional physics ceases to function. Some have speculated that these singularities might bridge to other universes, a conjecture veiled in mathematical possibility, but devoid of experimental validation. No signal, no probe, no particle can return from beyond the event horizon to offer insight into what lies within. Despite this veil of secrecy, astronomers estimate that our Milky Way harbors millions of black holes, though their small size makes them elusive. To date, only a fraction have been definitively identified. Yet, these stellar black holes are merely the lesser siblings of a far grander and more enigmatic phenomenon, the supermassive black holes that reside at the heart of every galaxy, including our own. These cosmic leviathans, millions or even billions of times the mass of the Sun, exert an influence on the evolution of galaxies themselves. Schwarzschild's wartime calculations, scribbled in the midst of battle, unlocked a gateway to one of nature's most astonishing secrets. His vision, once an obscure mathematical prediction, has since become one of the most captivating and well-substantiated pillars of modern astrophysics. And yet, even a century later, the depths of the black hole remain as unknowable as the darkness from which it draws its name. Supermassive. On April 10th, 2019, an image spread across the world at an unprecedented speed, capturing the imagination of both the scientific community and the general public. It was not a conventional work of visual grandeur, nor an intricate mosaic of detail. Rather, it was a blurred, indistinct torus of glowing orange against the vastness of an inky black void. Yet, despite its simplicity, this image was nothing short of revolutionary. It was the first direct image of a black hole, an object long theorized but never before glimpsed beyond the realm of mathematical abstraction. For centuries, black holes had remained elusive, their existence inferred only through indirect observations. Their very name is indicative of their nature. They are black by definition, absorbing all light and offering no direct visibility. Capturing an image of such an entity seemed, at first glance, to be an exercise in futility. Yet, scientists, armed with an understanding of the extreme gravitational effects black holes exert on their surroundings, devised a novel approach. A sufficiently massive black hole, enshrouded by a disk of superheated gas and dust, should radiate intensely in the radio spectrum. Given the right conditions, and with a telescope of sufficient size, this radiation could be detected. However, the black holes capable of generating such a detectable signal would have to be immense, far larger than stellar remnants. These objects, known as supermassive black holes, contain millions to billions of times the mass of our Sun and are thought to reside at the centers of nearly all large galaxies. Not only do they dominate the gravitational landscape of their host galaxies, but they may also play a critical role in their formation and evolution. Paradoxically, even as they devour surrounding material, these behemoths can influence star formation through their outflows, dispersing energy and matter across interstellar space. The fundamental nature of this relationship has led to one of the most perplexing questions in modern astrophysics. Did galaxies create their supermassive black holes, or did supermassive black holes, in some primordial form, seed the first galaxies? To uncover the secrets of these celestial giants, scientists turned first to the heart of our own Milky Way. Here, at a distance of approximately 25,000 light-years from Earth, lurks Sagittarius A*, a supermassive black hole with a mass of roughly 4 million suns. Its proximity made it an attractive observational target, but it came with unique challenges. Nestled deep within the dense core of our galaxy, Sagittarius A* is obscured by countless stars, cosmic dust, and interstellar gas. Furthermore, its relative motion across the sky due to the Earth's rotation posed additional difficulties in obtaining a long enough exposure for a detailed image. Instead, researchers focused their initial efforts on a more distant, yet more accommodating candidate, the supermassive black hole at the heart of the galaxy Messier 87. Situated 55 million light-years away in the Virgo cluster, M87's black hole dwarfs Sagittarius A*, containing an astonishing 6.5 billion solar masses. Despite its immense distance, its sheer size and the relative stability of its position in the sky made it an ideal subject for observation. The fundamental problem of imaging a black hole lies in resolution. In radio astronomy, the ability to resolve fine details is dictated by the size of the telescope aperture. To observe an object as distant and small as M87's event horizon, a telescope would need to be approximately the size of Earth itself, an apparent impossibility. The solution was both elegant and ambitious. Rather than constructing a single enormous telescope, scientists linked together an array of radio observatories scattered across the globe. This network, known as the Event Horizon Telescope, spanned from the South Pole to Spain, creating a virtual telescope with an effective aperture nearly as large as Earth. By precisely synchronizing observations from these facilities using atomic clocks, the EHT was able to collect vast amounts of data over 4 days in April 2017. Given the immense volume of information recorded, conventional data transfer methods proved inadequate. Instead, the data was stored on physical hard drives and transported to central processing centers, where teams of scientists meticulously reconstructed the image using advanced computational algorithms. After 2 years of rigorous data analysis, the result was unveiled: the first ever image of a black hole's event horizon, silhouetted against the glowing emissions of its surrounding accretion disk. The discoveries did not end with M87. In May 2022, after another 3 years of data processing, astronomers achieved a second milestone: the first image of Sagittarius A*. Despite its smaller mass compared to M87's black hole, its close proximity allowed for unprecedented insight into the structure of our own galaxy's central behemoth. This marked yet another step toward understanding the enigmatic nature of supermassive black holes. Despite these groundbreaking achievements, the question of supermassive black hole formation remains largely unresolved. How does an object grow to billions of solar masses? Some hypotheses suggest that these behemoths began as stellar mass black holes, gradually accumulating mass over billions of years through accretion and mergers. However, this explanation struggles to account for the existence of quasars, supermassive black holes observed less than 1 billion years after the Big Bang. Given the constraints of star formation in the early universe, these objects appear inexplicably massive far too soon. One proposed alternative is the existence of direct collapse black holes. Rather than forming from the remnants of dying stars, these black holes would emerge directly from the collapse of vast clouds of primordial gas. This mechanism circumvents the time constraints of gradual accretion but remains largely theoretical, as the specific conditions required for such a process to occur remain uncertain. Even more enigmatic are the so-called ultramassive black holes, such as TUN 618, which tips the scales at an astonishing 66 billion solar masses. Such giants challenge even the most generous growth models. Given that they shine as quasars, among the brightest objects in the universe, it is clear that they continue to accrete vast amounts of matter, shaping the very galaxies in which they reside. Yet, their sheer scale defies easy explanation. The final puzzle piece. As astronomers continue to refine their observations and models, one overarching mystery remains: the existence of massive black holes in the infant universe. Their presence so soon after the Big Bang suggests that our understanding of cosmic evolution is incomplete. If black holes truly require the deaths of massive stars to form, then a paradox emerges. There simply wasn't enough time for such stars to live and die in sufficient numbers. This enigma suggests that something fundamental is missing from our models. Was there an unknown mechanism that accelerated black hole formation in the early universe? Did exotic physics play a role? Or was there an undiscovered process that allowed black holes to bypass traditional growth pathways altogether? Somewhere in the depths of the cosmos, buried in the light of ancient quasars, the answers await. Whether through new observations, theoretical breakthroughs, or the next generation of telescopes, we stand on the precipice of unraveling the final secrets of these supermassive titans. What force sculpted these behemoths before the first stars were born? That, perhaps, is the next great question of modern astrophysics. Before atoms. In 1962, a 20-year-old undergraduate at Oxford University suffered what seemed at first to be an innocuous accident. He fell down a flight of stairs. His doctors dismissed it with casual advice: lay off the beer. But when his clumsiness persisted into the following year, his family grew increasingly concerned, and the young scholar was admitted to the hospital for an exhaustive series of medical tests. After 2 weeks of rigorous examinations, the physicians remained vague. They offered no definitive diagnosis, only a grim prognosis. His condition was atypical, it was expected to worsen, and they harbored little hope. The student himself did not press them for details. He simply took the vitamins they prescribed, though he could see in their eyes that they did not expect them to help. That student was Stephen Hawking. The diagnosis he had avoided confronting was a myotrophic lateral sclerosis, a neurodegenerative disease that progressively destroys motor neurons, leading to paralysis and, eventually, the loss of the ability to speak, swallow, and breathe. Doctors predicted that he had no more than 2 years to live. Hawking, however, defied those expectations. Rather than fading away, he continued his studies, taking his prescribed vitamins and persevering for 55 more years. Over the next half-century, he not only completed his postgraduate work, but became one of the most celebrated scientists of all time. His groundbreaking contributions to cosmology placed him among the ranks of Charles Darwin and Albert Einstein, and he became one of the youngest scholars ever elected a Fellow of the Royal Society. Yet, to much of the public, he remained as famous for his triumph over ALS as for his scientific achievements. But it was his science that earned him his place in history. Over the course of his career, Hawking fundamentally reshaped our understanding of black holes, the early universe, and the fundamental laws of physics. His work illuminated both the vast and the infinitesimal, and in doing so, he tackled one of the most profound questions in cosmology: what happened before atoms existed? Hawking's doctoral thesis, completed in 1966 in the shadow of his recent diagnosis, explored the great debate of the time: the origin of the universe. Inspired by the theoretical physics of black holes, he proposed that a similar mathematical singularity could describe the beginning of the cosmos itself. If black holes were born from the gravitational collapse of massive objects into an infinitely dense point, could the universe itself have emerged from such a state? Throughout the 1970s, Hawking made critical advances in our understanding of black holes. He formulated the area theorem, demonstrating that the event horizon of a black hole could never shrink. Later, in an effort to reconcile general relativity with quantum mechanics, he proposed that black holes might not be entirely black after all. Instead, he suggested they emit radiation, now known as Hawking radiation, allowing them to lose mass and eventually evaporate. Though this idea remains unconfirmed by direct observation, its theoretical implications have transformed our understanding of gravity, thermodynamics, and quantum mechanics. Yet, even as he explored the mysteries of black holes, Hawking remained captivated by the early universe. His investigations into singularities naturally led him to consider the Big Bang itself. If black holes informed our understanding of the fabric of space-time, then they could also offer clues about the first moments of existence. In 1971, Hawking put forth a radical idea that in the earliest epochs of the universe, a new type of black hole could have formed, not from the collapse of stars, but from the very birth of the cosmos itself. These were the so-called primordial black holes, a theoretical class of black holes that could have emerged in the first fractions of a second after the Big Bang. The story of the cosmos begins 13.8 billion years ago in an unimaginably hot and dense state. In its first instance, the universe was nothing more than a turbulent sea of energy fields, lacking the distinct forces we recognize today. As it cooled and expanded, these fields began to differentiate, giving rise to the fundamental forces that govern the universe. gravity, electromagnetism, and the nuclear interactions. With further cooling, the first subatomic particles, quarks and leptons, emerged, acquiring properties such as mass and charge. However, the universe remained far too hot and chaotic for stable atomic structures to form. Then came inflation, a brief but explosive period in which the universe expanded exponentially, doubling in size roughly 90 times in the span of 100 billionths of a second. This expansion magnified tiny quantum fluctuations into vast variations in the density of matter and energy, seeding the large-scale structure of the cosmos. Hawking saw an additional consequence of these fluctuations. Where there was excess density, there was increased gravity. As certain regions of the young universe became denser than their surroundings, their gravity caused them to collapse in upon themselves, triggering a runaway process that resulted in the formation of primordial black holes. These black holes would have been vastly different from those formed by collapsing stars. Instead of marking the end of stellar life cycles, they would have emerged at the very beginning of time. Their sizes would have depended on the moment of their formation. Those born earlier would have been minuscule, some no heavier than a paperclip, while those forming later could have rivaled the mass of thousands of suns. Mathematically, primordial black holes remain a compelling possibility. However, proving their existence is a far greater challenge. Unlike their stellar mass or supermassive counterparts, these ancient black holes would not necessarily be surrounded by accretion disks or emit detectable radiation. If they were formed in significant numbers, they could constitute a portion of dark matter, influencing the cosmos through their gravitational effects. Some have speculated that primordial black holes could explain mysterious astronomical phenomena, such as certain gravitational wave detections or even the formation of supermassive black holes in the early universe. Yet, detecting them remains a formidable task. When and where they formed, how numerous they were, and what sizes they likely reached are still open questions. The search for these ancient singularities is akin to seeking a needle in a cosmic haystack. But Hawking's legacy endures in the pursuit of these questions. His mathematics, elegant and unyielding, suggests that primordial black holes could very well have been among the first structures in the universe. The challenge now lies in proving it. As observational techniques advance, the possibility of detecting their subtle gravitational fingerprints grows ever more tantalizing. And so, the quest continues, not just to understand black holes, but to peer deeper into the earliest moments of the universe itself. What existed before atoms? If Hawking's vision was correct, then lurking in the fabric of the cosmos are remnants of a time before time, waiting to reveal the true origins of everything we see today. Finding the Needle. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, the 8 major planets of our solar system. Some have been observed since antiquity, their motions recorded by ancient astronomers who tracked their paths across the night sky with the naked eye. Others were discovered with telescopes, their existence predicted by the subtle gravitational tugs they exerted on their neighbors before finally being confirmed through direct observation. But even after 4,000 years of astronomical study, there are still unresolved mysteries lurking at the edge of our celestial neighborhood. One of them is the lingering possibility that yet another significant body remains hidden in the outer reaches of the solar system. In 1951, astronomer Gerard Kuiper pondered a fundamental question about comets. Scientists had long observed short-period comets, icy bodies that sweep through the solar system on highly elongated orbits, returning every 200 years or less. Halley's Comet, which last appeared in 1986 and will return in 2061, is among the most famous. Yet, every time such a comet passes near the Sun, it loses some of its icy mass to sublimation. Over time, these comets should have been completely depleted. Given the solar system's age, roughly 4.5 billion years, it seemed implausible that short-period comets could still exist unless there was a vast reservoir of icy bodies beyond Neptune, replenishing the cometary population. Kuiper proposed that such a belt of frozen objects must exist, periodically disturbed by gravitational interactions with Neptune and the other giant planets, sending some inward to become comets on their terminal trajectories toward the Sun. Yet, despite his hypothesis, it wasn't until 1992 that observational evidence confirmed its existence. After 5 years of searching beyond Neptune, astronomers detected the first Kuiper Belt object. More soon followed, revealing a previously unknown population of icy bodies. But as astronomers cataloged more KBOs, an anomaly emerged. Some of these distant bodies followed highly unusual orbits. One such object, the dwarf planet Sedna, discovered in 2003, follows a long, elliptical orbit that takes over 10,000 years to complete. Even at its closest approach, Sedna remains more than twice as far from the Sun as Neptune, meaning that Neptune's gravitational influence alone cannot account for its extreme trajectory. Moreover, other trans-Neptunian objects display a striking clustering effect, aligning their orbits in a way that statistical models suggest should be random. Over hundreds of millions of years, their orbits should have scattered chaotically. The fact that they have not implies the presence of an unseen force shaping their motion. In 2012, Brazilian astronomer Rodney Gomes proposed a provocative solution, a distant, massive planet acting as a gravitational shepherd, exerting its influence from the solar system's outermost frontier. This theoretical world, dubbed Planet 9, would have a mass approximately 6 times that of Earth and follow an elongated orbit about 400 times farther from the Sun than Earth. Despite knowing where to search, however, astronomers have yet to detect Planet 9 directly. Some skeptics argue that the observed orbital anomalies are simply artifacts of observational bias. NASA's then chief scientist Jim Green, quoting Carl Sagan, cautioned, "Extraordinary claims require extraordinary evidence." And yet, the mystery persists. But what if Planet 9 is not a planet at all? What if it has all the mass and gravitational influence predicted by the orbital calculations, yet is something much smaller and much stranger, a primordial black hole? If such an object existed, its event horizon would be no larger than a tennis ball, making it effectively invisible against the vastness of space. It would not reflect light, nor emit detectable radiation in the visible spectrum, eluding even our most powerful telescopes. This might explain why it has remained undetected despite extensive searches. Detecting such a small but powerful object requires an entirely different approach. One possibility is that its intense gravity might attract a surrounding microhalo of dark matter. On a galactic scale, dark matter is thought to form vast halos around entire galaxies, helping to maintain their rotational structure. If a miniature version of this phenomenon surrounds a primordial black hole, then detecting the radiation from interacting dark matter could provide a means of identification. However, this method depends on the unresolved nature of dark matter itself. Despite comprising an estimated 27% of the universe's total mass energy content, outweighing normal matter 6-1, dark matter has never been directly observed. Its existence is inferred from its gravitational effects, yet no instrument has ever been able to detect it directly. Two competing hypotheses attempt to explain dark matter's composition. One suggests that it consists of weakly interacting massive particles, a class of theoretical subatomic particles that interact gravitationally but otherwise evade detection by existing physics models. The other posits the existence of massive astrophysical compact halo objects, which could include dense, invisible astronomical bodies such as black holes. Among the earliest proponents of the macho hypothesis was Stephen Hawking, who speculated that primordial black holes formed in the first moments of the universe could contribute significantly to the missing dark matter. If true, then the dark matter that binds galaxies together is not merely dark in the figurative sense, unknown and unseen, but dark in the literal sense, comprised of countless black holes formed in the first second of cosmic history. If primordial black holes are indeed abundant, then much of the matter that came into existence at the birth of the universe may have been instantly imprisoned behind event horizons, never to reemerge. Only a fraction, 1/6, by current estimates, escape this fate to form stars, planets, and the observable universe as we know it. The implications are profound. If Planet 9 is a primordial black hole, then it represents not just an anomaly in our solar system, but a window into the physics of the very early universe. Finding it would not only resolve a long-standing astronomical mystery, but also provide crucial insights into the origins of dark matter and the fundamental nature of space-time. So, how does one detect a black hole the size of a tennis ball hiding in the vastness of space? That is the challenge that now faces astronomers. Whether through indirect gravitational influences, interactions with dark matter, or novel detection techniques yet to be devised, the search for this missing piece of our cosmic puzzle continues. One fundamental concept in modern astrophysics relies on a prediction made by Stephen Hawking, Hawking radiation. This theoretical phenomenon, arising at the event horizon of black holes, is a product of quantum particle interactions subjected to the overarching framework of general relativity. According to Hawking's calculations, black holes are not entirely black, but rather emit a faint stream of radiation, akin to a gamma-ray glow. Over vast timescales, this radiation leads to the gradual evaporation of black holes. Crucially, Hawking predicted that the smaller a black hole's event horizon, the more rapidly it will evaporate, culminating in an exponential increase in radiation that ultimately results in a catastrophic explosion. The implications of this theory are profound. If black holes with masses below kilograms had formed in the early universe, they would have decayed within a timescale shorter than the universe's current age. Consequently, astronomers have sought evidence of these theoretical remnants, scanning the cosmos for their final explosive emissions. The Fermi Gamma Ray Space Telescope, launched in 2008, has been one of the most sophisticated tools in this endeavor. However, after nearly 15 years of continuous observation, no definitive signals of such primordial black hole explosions have been detected. This absence of observational evidence serves as a critical constraint on the role of primordial black holes in the cosmos. Specifically, it suggests that less than 1% of dark matter can be attributed to these hypothetical entities. Such a result raises a tantalizing question. Was Hawking's reconciliation of quantum mechanics and general relativity incorrect? The entire framework of Hawking radiation rests on intricate theoretical calculations, yet no empirical data has decisively confirmed its existence. Beyond direct gamma-ray searches, astronomers have explored alternative detection methods rooted in gravitational effects. If primordial black holes were abundant, their gravitational influence would periodically distort the light from distant stars, a phenomenon known as gravitational microlensing. Likewise, gamma rays from pulsars or supernovae might flicker unpredictably if a primordial black hole passed between Earth and the source. However, exhaustive surveys in both optical and gamma-ray astronomy have failed to produce compelling evidence of such events. These results impose additional constraints on the abundance of primordial black holes, particularly those with masses comparable to or smaller than Earth. Further indirect limits arise from astrophysical considerations. If primordial black holes were plentiful, they would occasionally capture and consume other dense objects, such as neutron stars and white dwarfs. The continued existence of these stellar remnants in large numbers suggests that such interactions have not been common, further restricting the possible prevalence of primordial black holes. Cosmologists have also turned their attention to the universe's earliest epochs in search of clues. If primordial black holes had formed shortly after the Big Bang, they would have influenced the distribution of matter in ways that should be imprinted in the cosmic microwave background. However, detailed analyses of the CMB have failed to reveal any such signatures for black holes in the mass range of 100 to 10,000 solar masses. If primordial black holes did exist, they must have been too small to leave detectable imprints on the primordial radiation field. For decades, these accumulating null results cast doubt on the viability of primordial black hole theory. However, in 2015, a breakthrough reignited interest in the idea. The Laser Interferometer Gravitational Wave Observatory detected the first ever direct observation of gravitational waves, traced back to the merger of two black holes, each with a mass approximately 30 times that of the Sun. This discovery confirmed the existence of gravitational waves, but also posed a perplexing astrophysical question. Where did these black holes come from? Black holes of this mass are difficult to explain through conventional stellar evolution models. They are too large to be the remnants of typical star deaths, yet too small to be classified as supermassive black holes. One intriguing possibility is that they are, in fact, primordial black holes. If primordial black holes commonly formed with masses in the 30 solar mass range, their predicted collision rates align remarkably well with the frequency of black hole mergers observed by LIGO. While earlier observational constraints ruled out primordial black holes as the dominant component of dark matter, they did not exclude their existence altogether. Instead, they have refined our understanding, placing strict limits on the possible mass ranges in which these objects might exist. Interestingly, there remain unexplored mass regimes where primordial black holes could still play a crucial role in cosmic evolution. Simulations suggest that if dark matter were partially composed of primordial black holes with masses around 1.4 solar masses, they could have significantly influenced the formation of the first stars, galaxies, and even supermassive black holes. The question of primordial black holes remains one of the most compelling mysteries in modern cosmology. Future observational efforts hold the potential to unlock new insights. The James Webb Space Telescope, with its unparalleled ability to observe the earliest galaxies, may provide indirect evidence of primordial black hole seeding. Meanwhile, the Laser Interferometer Space Antenna, a next-generation space-based gravitational wave observatory set to launch in the 2030s, will be capable of detecting the signatures of black hole mergers at an unprecedented level of detail. Stephen Hawking's pioneering insights into black holes opened a new frontier in theoretical physics, and the search for primordial black holes continues to push the boundaries of our understanding. Whether they prove to be key players in the universe's earliest moments or remain elusive relics of theoretical physics, their study holds the potential to answer fundamental questions about dark matter, galaxy formation, and the very nature of space-time itself. The quest to uncover their secrets is, in essence, a quest to illuminate the deepest mysteries of the cosmos.
The dawn of a new age, the Trinity test, and the birth of modern physics. What lies within the smallest building blocks of the universe? Can the tiniest particles hold the power to reshape history and redefine the very fabric of civilization? These questions, once the domain of philosophers and speculative thinkers, gained terrifying clarity in the pre-dawn hours of July 16, 1945, when science unlocked one of nature's most devastating secrets. In the barren expanse of a New Mexico desert, the first light of dawn struggled to rise above the horizon. 30 minutes before sunrise, the stars had already surrendered to a shadowless blue hue suffusing the desert floor. The stillness was deceptive. This unassuming patch of ground had been meticulously prepared for a singular moment in history. Rising alone at the base of the Oscura Mountains, a 30-meter steel tower bore an ominous payload at its apex. Surrounding it, at precise intervals 9 kilometers away, 3 partially buried shelters housed a mix of soldiers and scientists awaiting the culmination of years of groundbreaking yet harrowing research. The air crackled with anticipation as a voice on the public address system began the countdown. Lying prone on the ground with their feet pointed toward the distant tower, the observers could not see the device itself. But they would soon witness its unimaginable power. At precisely 5:30 a.m., the quiet was shattered by an earth-shaking explosion. The steel tower evaporated, the desert floor melted into green glass, and the dim light of dawn was instantly overwhelmed by a searing brilliance that turned night into day. This was the Trinity test, the first full-scale detonation of a nuclear bomb. It marked the dawn of a new era in human history, one that would shape geopolitics, scientific discovery, and humanity's perception of its place in the universe. The events leading to Trinity began decades earlier, in a time when the atom was merely a theoretical curiosity. For centuries, philosophers and early scientists had debated whether matter could be infinitely divided or if there existed fundamental, indivisible units. By the early 20th century, experiments had revealed that atoms were not the ultimate building blocks of matter. Instead, they contained even smaller constituents, nuclei surrounded by electrons. The discovery of the nucleus opened the door to a new understanding of energy and matter. In 1938, German chemists Otto Hahn and Fritz Strassmann, along with physicists Lise Meitner and Otto Frisch, discovered nuclear fission, the splitting of an atomic nucleus into smaller fragments, accompanied by a staggering release of energy. This revelation coincided with the outbreak of World War II, and the implications of harnessing such power were immediately apparent. Albert Einstein, along with physicist Leo Szilard, penned a letter to President Franklin D. Roosevelt, warning that Nazi Germany might develop a powerful new weapon based on nuclear fission. This letter spurred the United States to initiate the Manhattan Project, an unprecedented effort to harness atomic energy for military purposes. The device tested at Trinity, nicknamed the Gadget, was a plutonium-based implosion bomb. Its design relied on carefully shaped explosives to compress a subcritical plutonium core into a supercritical state, triggering a chain reaction. This reaction released energy equivalent to 21,000 tons of TNT within a fraction of a second. The result was both a triumph of human ingenuity and a chilling demonstration of the destructive potential of nuclear science. The explosion not only vaporized the steel tower but also left a crater at the site, its floor transformed into a sheet of green, glassy material later named trinitite. Above the desert, a massive fireball ballooned upward, forming the now iconic mushroom cloud, a grim symbol of the nuclear age. If not for the exigencies of World War II, nuclear science might have taken a slower and more measured path. Before the war, the exploration of the atom was a niche pursuit, limited to small advancements and incremental discoveries. The pressures of wartime, however, accelerated this research, transforming atomic science into a cornerstone of modern physics. The success of the Trinity test marked a turning point, not only in military history but also in humanity's understanding of the universe. The same principles that unleashed the bomb's power inspired a deeper inquiry into the nature of matter and energy. The atom was no longer just a fundamental particle, it was a gateway to a hidden world of fields, forces, and particles, where the rules of classical physics gave way to the strange and counterintuitive laws of quantum mechanics. As the glow of Trinity faded, it left behind more than a mark on the desert floor. It ignited a scientific revolution. What are the true building blocks of the universe? How does energy shape matter at its most fundamental level? These questions propelled scientists deeper into the quantum realm and further back in time, seeking to unravel the mysteries of creation itself. The discovery of nuclear fission was just the beginning. The journey to understand matter led to the exploration of subatomic particles, the development of quantum field theory, and the realization that our universe operates on a tapestry woven from particles and waves, probabilities and uncertainties. This quest for understanding culminated in the discovery of the Higgs boson in 2012, a particle predicted decades earlier but only recently observed, a testament to humanity's relentless curiosity and determination. Trinity also raised profound philosophical questions. At its most fundamental level, what is reality? The principles of quantum mechanics suggest that particles exist in states of probability until observed, challenging our classical notions of objectivity and permanence. Is the universe we perceive a reflection of deeper, hidden truths? Or is it an emergent phenomenon, shaped by forces and dimensions beyond our comprehension? The legacy of the Trinity test is both inspiring and sobering. It marked the moment when humanity wielded the power to alter the fabric of reality, for better or worse. The knowledge it brought has driven advancements in energy, medicine, and material science, while also highlighting the ethical responsibilities that come with such power. The journey to understand the universe continues. From the splitting of the atom to the discovery of the Higgs boson, each breakthrough brings us closer to answering the age-old question, what is everything made of? And, perhaps more profoundly, what does it mean to truly understand the cosmos? As we continue to explore, we must remember the lessons of Trinity. The pursuit of knowledge is a double-edged sword, capable of both great good and unimaginable harm. It is up to us to wield it wisely, ensuring that the legacy of our discovery serves not just science, but humanity as a whole. Splitting the atom, a journey through science and philosophy. The origins of these inquiries date back to the ancient Indian philosophers of the 8th century BCE. They proposed a radical idea: nothing we perceive is truly real. Their extreme reductionist philosophy dismantled the world into its fundamental components. A cart, for instance, could be reduced to wheels, axles, and a yoke. Each of these, in turn, could be further dissected into smaller parts, until nothing remained but tiny, indistinguishable specks. What, then, are the objects of our experience? Are they merely assemblages of these specks, arranged to give the illusion of substance? This existential puzzle resurfaced centuries later among ancient Greek philosophers. Democritus and Leucippus, reflecting on the same problem, concluded that everything could be broken down repeatedly until an ultimate, indivisible unit was reached. They named these fundamental units atomos, meaning uncuttable. This profound concept laid the groundwork for a scientific journey that would span over 2 millennia. The transition from philosophical speculation to scientific inquiry began in earnest in the 19th century. John Dalton, an English chemist, synthesized ancient philosophies with contemporary scientific observations to formulate a groundbreaking theory. Dalton's work revolved around the analysis of chemical compounds. Each compound, he observed, behaved in unique and predictable ways. Methane, for example, consisted of carbon and hydrogen atoms, while nitrous oxide contained nitrogen and oxygen atoms. Dalton postulated that these compounds were constructed from indivisible building blocks, or atoms, specific to each element. Dalton's theory introduced the scientific concept of the atom, aligning with the ancient notion of atomos. Yet, as the 19th century unfolded, evidence began to challenge the idea of indivisibility. Atoms, it seemed, harbored secrets far more complex than Dalton or the ancients could have imagined. By the late 1800s, experiments probing the nature of electric charge unveiled a new kind of particle. J.J. Thomson, an English physicist, identified the electron in 1897, a negatively charged particle capable of moving independently of atoms. This discovery raised profound questions. If electrons were part of atomic matter, how could atoms remain indivisible? Ernest Rutherford provided a critical piece of the puzzle. In his famous gold foil experiment, Rutherford bombarded a thin sheet of gold with radioactive particles. To his astonishment, some particles rebounded, while others passed straight through. This led him to propose a revolutionary atomic model. Atoms consist of a dense, positively charged nucleus surrounded by orbiting electrons. Rutherford identified protons within the nucleus as carriers of positive charge, establishing the atom as a composite structure. While Rutherford's model explained much, it left one glaring inconsistency: the mass of certain atoms exceeded the combined mass of their protons and electrons. James Chadwick resolved this mystery in 1932 by discovering the neutron, a neutral particle residing within the nucleus. Chadwick's work earned him a Nobel Prize and deepened our understanding of atomic structure. With protons, neutrons, and electrons identified, the atom's indivisibility had been decisively disproven. The discovery of the neutron catalyzed a new era in atomic research. Scientists bombarded atomic nuclei with neutrons, altering their composition and occasionally splitting them. In 1938, Austrian physicist Lise Meitner, collaborating with Otto Hahn and Fritz Strassmann, identified this process as nuclear fission. A single neutron could split a uranium atom into smaller nuclei, releasing an immense amount of energy. Meitner's insights were groundbreaking. She named the phenomenon fission, drawing an analogy to cell division in biology. However, her pivotal contributions were overshadowed by sexism and anti-Semitism, leaving Hahn to receive sole recognition in the 1944 Nobel Prize. The practical implications of fission were profound and terrifying. Scientists quickly realized that a chain reaction of atomic splits could unleash unprecedented destructive power. This realization culminated in the development of the atomic bomb, marking a turning point in human history. The detonation over Hiroshima in 1945 underscored the dual-edged nature of scientific discovery, the potential for both immense progress and unparalleled destruction. With the atom split, the quest for fundamental particles intensified. Protons and neutrons, previously thought to be indivisible, were revealed to consist of smaller components called quarks. Electrons belonged to a different category of particles known as leptons. These discoveries expanded our understanding of matter's building blocks, but they also introduced new mysteries. Were quarks and leptons truly fundamental, or would further exploration uncover even smaller particles? The 20th century's advances in particle physics aimed to unify our understanding of matter. The Standard Model emerged as a framework, categorizing particles and describing their interactions. Yet, significant questions remained unanswered. For instance, what accounts for the vast majority of the universe's mass and energy? The discovery of dark matter and dark energy hinted at realms beyond the Standard Model, suggesting that the journey of exploration is far from over. As we probe deeper into the fabric of the cosmos, we find ourselves circling back to the questions posed by ancient philosophers. What is the nature of reality? Are the particles we observe the ultimate constituents of matter, or are they merely steps on an infinite ladder of discovery? Science and philosophy, once distinct domains, converge in their shared pursuit of these profound truths. The splitting of the atom represents both a triumph of human ingenuity and a cautionary tale. It highlights our capacity to unravel nature's deepest secrets and the responsibility that comes with such knowledge. As we stand on the shoulders of giants, from Democritus to Meitner, we are reminded of the boundless potential of human curiosity and the ethical imperative to wield our discoveries wisely. The story of the atom is far from complete. It is a testament to the enduring quest to understand our universe, a journey that continues to inspire, challenge, and transform humanity. Deeper we go, the story of quarks and the particle zoo. What lies beneath the surface of matter? Could there exist something smaller, something more fundamental than the atoms we once believed to be the indivisible building blocks of the universe? And if so, how deep does the rabbit hole go? These questions have driven the scientific imagination for decades, pushing the boundaries of our understanding of the cosmos and ourselves. This story begins not with laboratory experiments or sophisticated machinery, but with words. James Joyce, the renowned Irish writer, sought immortality through his literary creations. Yet, even in his wildest dreams, he could not have foreseen how his work, particularly Finnegan's Wake, would echo beyond the realm of literature and into the world of particle physics. Joyce's novel, famously dense and cryptic, captured the imagination of a young American physicist named Murray Gell-Mann, who would draw inspiration from its lines to name one of the most fundamental constituents of matter, the quark. By the mid-20th century, physicists had already cracked open the atom, revealing its subatomic constituents, protons, neutrons, and electrons. However, advances in technology soon uncovered a bewildering array of other particles, collectively referred to as the particle zoo. This term captured both the excitement and confusion of a field that suddenly seemed overrun with exotic inhabitants. Among these were hadrons, particles with mass, including protons and neutrons, as well as their more exotic cousins like pions and kaons. The proliferation of hadrons presented a puzzle. While each particle had its own unique properties, there were undeniable similarities between them. Why were they distinct yet fundamentally alike? This enigma echoed the earlier challenge of understanding the periodic table of elements, which had eventually been resolved by uncovering the atomic structure of matter. Physicists now sought a similar unifying explanation for the hadrons. In the 1960s, two physicists working independently arrived at a groundbreaking hypothesis. Murray Gell-Mann, based at the California Institute of Technology, and George Zweig, working at CERN in Switzerland, proposed that hadrons were not fundamental after all. Instead, they were composed of even smaller particles. Gell-Mann envisioned 3 subhadronic particles and whimsically named them quarks, borrowing the term from a line in Finnegan's Wake, 3 quarks for muster mark. Meanwhile, Zweig imagined 4 such components, which he called aces, drawing inspiration from the suits in a deck of cards. Both models provided a compelling framework for understanding the particle zoo. However, these ideas were purely theoretical until experimental evidence could confirm the existence of these subhadronic entities. The Stanford Linear Accelerator Center, established in the mid-1960s, became the proving ground for these bold hypotheses. At 3.2 kilometers long, SLAC's linear accelerator was the longest of its kind, capable of accelerating electrons to energies of 50 gigaelectron volts. By colliding these high-energy electrons with protons and neutrons, physicists could study the wreckage and glean insights into the subatomic structure of matter. In 1968, experiments at SLAC provided the breakthrough. The collisions revealed point-like particles within protons, consistent with Gell-Mann's theoretical quarks. These results confirmed that protons, like atoms before them, were not indivisible. Quarks were real, and they represented a new frontier in our understanding of matter. With the existence of quarks established, the next challenge was to determine their properties and varieties. Over the following decades, high-energy experiments and theoretical advancements identified 6 distinct types, or flavors, of quarks: up, down, strange, charm, top, and bottom. Each flavor possesses unique characteristics, including electric charge, mass, spin, and a property intriguingly named color. The term color in this context has nothing to do with visual hues but instead describes the way quarks interact via the strong nuclear force. This force, mediated by particles called gluons, binds quarks together to form hadrons. Quarks combine in triplets to create baryons, such as protons and neutrons, or in pairs to form mesons. These combinations follow strict rules dictated by quantum chromodynamics, QCD, the theory describing the behavior of quarks and gluons. Quarks are the foundation of all baryons and mesons, which in turn make up the nuclei of atoms. Protons, composed of 2 up quarks and 1 down quark, carry a positive charge. Neutrons, consisting of 2 down quarks and 1 up quark, are electrically neutral. Together, they form the nuclei of every element in the periodic table, giving rise to the diversity of matter in the universe. But quarks do not only form stable particles. In high-energy environments, such as those created in particle accelerators or cosmic events, quarks can also combine into exotic particles like lambda, sigma, and 11 baryons, as well as fleeting mesons. These particles often exist for mere fractions of a second, yet their study provides invaluable insights into the behavior of the strong nuclear force and the early moments of the universe. Quarks are not the only fundamental particles in the standard model of particle physics. Leptons represent another category of elementary particles, including the familiar electron as well as the heavier muon and tau particles. Each lepton also has an associated neutrino, a nearly massless and electrically neutral particle. Together, quarks and leptons form the building blocks of all known matter. Their interactions, governed by the fundamental forces of nature, underpin the structure and dynamics of the cosmos. Yet, the Standard Model, despite its success, leaves many questions unanswered. For all its elegance, the Standard Model does not explain everything. Why do particles have mass? The discovery of the Higgs boson in 2012 provided a partial answer, demonstrating how particles acquire mass through interactions with the Higgs field. Yet, the origins of the Higgs field itself remain a mystery. Moreover, the Standard Model cannot account for dark matter and dark energy, which together constitute approximately 95% of the universe's mass-energy content. Nor does it provide a unified framework for reconciling quantum mechanics with general relativity, the theory describing gravity. As we probe deeper into the nature of matter, we find ourselves revisiting the fundamental questions that have inspired humanity for centuries. Are quarks and leptons truly indivisible, or will future experiments uncover even smaller constituents? Is there a single, elegant theory that can unify all the forces of nature, from the strong nuclear force to gravity? The journey into the subatomic realm has already transformed our understanding of the universe. It has revealed a world of extraordinary complexity and beauty, governed by rules that challenge our intuition yet hold the key to understanding the cosmos. And as we stand on the brink of new discoveries, one thing is certain: the deeper we go, the more there is to learn. The mystery of matter, the hunt for the Higgs boson. What gives matter its substance? Why do particles have mass, and how did they acquire it in the first place? Without mass, electrons would not bind to protons, hydrogen atoms would not form, and the universe as we know it would be a lifeless void. These questions are not only fundamental to our understanding of physics, but also vital to comprehending the very fabric of the cosmos. February in Chicago is harsh. The wind, sharp and relentless, barrels through the streets, carrying the icy breath of Lake Michigan and depositing snow in corners of the bustling city. Yet, amidst the frigid air, the atmosphere inside the American Association for the Advancement of Science's 2009 annual meeting was anything but cold. Scientists gathered with anticipation, drawn to a singular lecture room where the hottest topic in particle physics was about to be discussed: the search for the Higgs boson, often dubbed the God particle. This was no ordinary scientific endeavor. It was a race, a contest of monumental stakes, pitting Fermilab's Tevatron in Illinois against CERN's Large Hadron Collider, LHC, straddling the French-Swiss border. The stakes were immense, as the Higgs boson was the missing piece of the standard model of particle physics, a framework describing the fundamental forces and particles shaping the universe. The LHC, a marvel of modern engineering, was purpose-built for this quest at a staggering cost of €3 billion. Yet, just a month after its inauguration in 2008, disaster struck. A catastrophic explosion damaged several magnets in the accelerator, necessitating over a year of repairs. This unforeseen setback handed Fermilab a golden opportunity to take the lead. At the 2009 conference, Fermilab's scientists presented their progress, cautiously optimistic yet candid about the challenges they faced. The search for the Higgs boson was like hunting for a needle in a haystack, with the added complication that no one knew exactly what the needle looked like. The Higgs boson wasn't an arbitrary goal, it was the key to resolving one of the most perplexing mysteries in physics: the origin of mass. The Standard Model, developed over the latter half of the 20th century, provided an elegant explanation for the fundamental forces of nature. It described four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces acted through specific particles known as gauge bosons. For instance, photons carried the electromagnetic force, while gluons mediated the strong nuclear force. W and Z bosons were responsible for the weak force, and a hypothesized graviton was theorized to explain gravity. Experiments confirmed the existence of most of these particles, cementing the Standard Model as a robust framework. However, one glaring issue remained: the question of mass. Quarks, the building blocks of protons and neutrons, had varying masses. The top quark, for example, was 75,000 times heavier than the up quark. Yet, the equations governing particle physics suggested that all particles should be massless. This contradiction was not merely a theoretical inconvenience, it had profound implications for the universe's evolution. Without mass, matter would never have coalesced into stars, galaxies, or life itself. The theoretical breakthrough came in 1964, when Peter Higgs and his contemporaries, Robert Brout and François Englert, proposed a radical solution. They suggested that in the early universe, particles emerged without mass. Soon after, a field, now known as the Higgs field, permeated the cosmos. Particles interacting with this field acquired mass, while others, such as photons, remained unaffected. The Higgs boson, a particle associated with this field, was theorized to exist as its physical manifestation. Finding this elusive particle became a central goal for physicists, for its discovery would confirm the mechanism that endowed the universe with mass. However, detecting the Higgs boson posed an enormous challenge. Its ephemeral nature meant it decayed almost instantly after being created in high-energy collisions, leaving behind a trail of particles that had to be meticulously analyzed. To generate the Higgs boson, scientists turned to particle accelerators, machines that collided particles at nearly the speed of light. The Tevatron, Fermilab's pride, was equipped to probe a specific energy range where the Higgs might appear. Meanwhile, the LHC, with its superior energy capacity and 27-kilometer circumference, was designed to search across a broader spectrum. After its repairs, the LHC resumed operations in 2010, marking the beginning of an intense period of experimentation. Protons collided within the massive detectors, generating unimaginable amounts of data. Analyzing this data required extraordinary computational power and collaboration among thousands of scientists worldwide. On July 4, 2012, CERN announced a momentous discovery. Two of the LHC's detectors, ATLAS and CMS, had independently detected a particle consistent with the Higgs boson. The data showed a clear signal at an energy of around 125 gigaelectron-volts, with a statistical confidence level high enough to declare it a discovery. Nearly 5 decades after it was first theorized, the Higgs boson had been found. Peter Higgs and Francois Englert received the Nobel Prize in Physics in 2013 for their contributions to this groundbreaking theory. The discovery not only completed the Standard Model but also marked a triumph of human ingenuity and perseverance. The Higgs boson now takes its place alongside the 60 other fundamental particles described by the Standard Model. These include the 6 flavors of quarks, 6 leptons, including the electron and neutrinos, and various gauge bosons. Together, they form the building blocks of matter and govern the interactions that shape the universe. However, the Standard Model, despite its success, is not the final word on the nature of reality. It cannot explain dark matter and dark energy, which make up 95% of the universe's mass-energy content. Nor does it reconcile quantum mechanics with general relativity. Moreover, the graviton, the hypothetical particle of gravity, remains elusive. The discovery of the Higgs boson is not the end of the story but a new beginning. Scientists now seek to answer questions that the Standard Model cannot. What is the true nature of dark matter? Are there undiscovered particles or forces that extend beyond the current framework? And can we achieve a unified theory that connects all the forces of nature? To explore these mysteries, physicists are pushing the boundaries of technology and imagination. Plans are underway for more powerful accelerators, such as the proposed Future Circular Collider, which would dwarf the LHC in size and energy capacity. Meanwhile, experiments in astrophysics and cosmology aim to shed light on dark matter and the origins of the universe. The discovery of the Higgs boson is a testament to the power of human curiosity and collaboration. It demonstrates how theoretical ideas, born of abstract mathematics, can lead to tangible discoveries that reshape our understanding of the cosmos. The Higgs field, an invisible yet omnipresent entity, serves as a reminder that even the most fundamental aspects of reality are often hidden from view, awaiting discovery by those bold enough to seek them. As we continue to probe the mysteries of matter, we stand on the threshold of a new era in physics. The journey from the subatomic to the cosmic is far from over, and the quest to understand the universe's deepest secrets promises to inspire generations to come. The Dawn of Matter, a journey into the fabric of the universe. What is the true nature of reality? Is matter, as we perceive it, an immutable building block of the cosmos? Or does it conceal a deeper, more enigmatic truth? From the grandest galaxies to the tiniest particles, the universe challenges us to peel back layer after layer, revealing a complexity that defies comprehension. And yet, as we delve deeper, we find ourselves confronting not just the mystery of matter but the very nature of existence itself. Physicists, armed with precise calculations, estimate the number of fundamental particles in the observable universe. The number is staggering, more than 3 vigintillion quarks and electrons, a 3 followed by 80 zeros. These particles constitute the protons and neutrons in hydrogen and helium atoms, as well as their associated electrons. Even with such a mind-boggling count, when spread across the vastness of space, they average to just 1 quark-sized particle per cubic meter. The universe, it seems, is not so much full of matter as it is dominated by emptiness. Yet, for all the particles we can count and measure, they make up only a small fraction of the cosmos. Matter as we know it, the stuff of stars, planets, and living beings, constitutes a mere 5% of the universe. The remaining 95% is an enigma. 25% is thought to be dark matter, a mysterious substance that holds galaxies together, while 70% is attributed to dark energy, the force driving the accelerating expansion of the universe. Though these phenomena remain poorly understood, the matter we can observe tells a story that stretches back to the very dawn of time. Rewinding the cosmic clock to the very beginning, we arrive at a moment of unimaginable density and temperature. A trillionth of a second after the Big Bang, the universe was governed by a single, unified force. The distinct forces we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were melded into one. Particles, as we understand them, did not yet exist. Instead, there was perhaps a single type of boson, a progenitor of all the particles to come. As the universe expanded and cooled, this symmetry broke. The unified force split into the strong, weak, and electromagnetic forces. Gluons, photons, and W and Z bosons emerged as the carriers of these forces. Yet, at this stage, these particles were massless, and their behaviors were indistinct. It was only after a relative eternity, a trillionth of a second, that the cosmos cooled sufficiently for the Higgs field to emerge. The Higgs field permeated space, endowing certain particles with mass as they interacted with it. Quarks, leptons, and bosons acquired distinct properties, setting the stage for the formation of the universe as we know it. However, the temperature was still too high for quarks to combine into protons and neutrons. Instead, they existed in a turbulent, high-energy state known as a quark-gluon plasma, a primordial cosmic soup. Over time, as the universe continued to expand and cool, quarks began to bind together, forming composite particles like protons and neutrons. These nucleons clustered to form atomic nuclei, which eventually captured electrons to create neutral atoms. Hydrogen and helium emerged as the first elements, and from these building blocks, the universe began its transformation into a complex tapestry of stars, galaxies, and planets. While this story of cosmic evolution paints a picture of ever smaller building blocks nestled within one another, quantum mechanics reveals a more unsettling truth. At the smallest scales, particles such as quarks, leptons, and bosons defy classical understanding. They exist simultaneously as particles and waves, described not by precise locations but by probability distributions. This quantum uncertainty means that particles cannot be pinned down in space and time, challenging the very concept of their existence. Quantum field theory provides an even deeper insight. According to this framework, particles are not standalone entities but rather excitations in underlying fields. The universe is crisscrossed by at least 24 distinct quantum fields, each corresponding to a fundamental force or particle. These fields interact, creating interference patterns that give rise to the semi-stable particles we observe. A proton, for example, is not a solid object but a dynamic interplay of quark and gluon fields, shaped by the strong nuclear force. This perspective transforms our understanding of matter. The tangible objects we perceive are merely manifestations of underlying fields. The Higgs field, electromagnetic field, and others weave an intricate web through space and time, their ripples and interactions giving rise to the illusion of solidity. In this view, the universe is not composed of discrete particles but of continuous, interacting fields, with matter emerging as a transient, localized phenomenon. Even as we unravel the story of matter, vast mysteries persist. Dark matter and dark energy, which dominate the cosmos, remain beyond the grasp of our current theories. The standard model of particle physics, though remarkably successful, cannot account for these phenomena. Nor does it explain the nature of gravity at the quantum level, leaving room for new frameworks that may unify our understanding of the universe. Indian philosophers, nearly 3,000 years ago, speculated that the material world was an illusion. Modern physics, in its exploration of quantum fields and probabilities, echoes this ancient intuition. The universe, at its most fundamental level, may be less a collection of particles and more a symphony of interacting waves and fields, their transient peaks shaping the reality we experience. As we continue to probe the nature of matter, we are reminded that every discovery opens new questions. The journey into the fabric of the universe is far from over, and the mysteries that remain promise to inspire and challenge humanity for generations to come.